Okay, so I have the pleasure of introducing Wesley Boelrijk. He is a senior data scientist at KLM, where he develops next-generation demand forecasting models. He's also a Formula One fan, and we'll be discussing how Formula One goes Bayesian. He's a third-time speaker, so let's please give him a warm welcome.
Thank you for the introduction. Welcome to the talk. Good afternoon. Nice to see so many of you here. Today we're here for the talk Formula One Goes Bayesian, Time Series Decomposition with PyMC. It's quite a big of a title. There's 3 components in it. And I'm just wondering who of you is here for the time series? Okay, that's quite some hands. Then time series goes Bayesian in this talk. So who is interested in the Bayesian part of the talk? All right, also a lot of hands. And who is here just for the Formula One content? Yeah, nice. I see some more fans. All right. Sorry?
All 3 is a golden combo.
Exactly. There we go. So today we're going to talk about how these things overlap, how we can use time series Bayesian to do a case study on Formula One, and learn about the framework that I'm presenting here, so how we can do this. Then, who am I? As I was introduced, I am a lead data scientist at KLM working on time series models, and I chose to do it the Bayesian way. Formerly, I was the lead ML engineer at Accelerated, where I trained and coached engineers and scientists, and I'm passionate about Formula One. This is me on the Formula One podium in Austria earlier this year when I attended the Grand Prix. So why would we want to model this? When we look at Formula One races, we see engineers on the pit walls doing all kind of stuff with data. They're constantly calculating stuff, coming up with the strategies, and trying to figure out what the best way to pursue the weekend is. Today we're going to look at a few questions. First of all, understand how fuel burn and track evolution works during the race. We're going to interpret the speed and degradation of different tire compounds. And maybe the oldest question in Formula One, is it the car or is it the driver? Let's have a look on the statistics of that. Why are we taking this framework? I think it's very flexible. We can include domain knowledge in our models. So the things that we already know about Formula One, we can apply them and use them in our models to do prediction, forecasting, and simulation of strategies. So, Bayesian. This is not going to be a talk on the fundamentals of Bayesian, but I'm going to use some of its terms, and I think it's good to be familiar with some of them. So we have prior, which is basically the before. It's the distributions that we choose as our starting points. After that, we do sampling or estimation, which is basically sampling from this prior distribution to evaluate the model fit and so learn the distributions. There's an algorithm to do this. It's called MCMC, Markov Chain Monte Carlo. And I think it's funny that Monte Carlo is both influential in Bayesian as in Formula One with the Monaco Grand Prix. When we've done this procedure, we end up with the posterior, the after, and here we obtain distributions for our parameters that we've just learned. And one of the nice things is that it includes the uncertainty in the distributions. Here we see an example. This can be a posterior distribution of a parameter mu. If we compare this to just the point estimate that we see at the bottom, we have a lot more information. We have the entire distribution and can see the variance in here, and therefore know how certain or uncertain we are. If we have another mu, can be the exact same point estimate, but with a more narrow distribution. So here we're more certain of where this parameter value approximately lies. Then about time series. I mentioned time series decomposition. What is that? Maybe you've heard of autoregression before. Here I put them as 2 separate things, how they differ from each other. Autoregression typically uses lags, where time series decomposition uses components, as it's in the name. Autoregression is more short-term focused, while decomposition is more on the long-term patterns. How can we learn them? For autoregression, you need stationarity. Sometimes you need to take the first differences to obtain that. Decomposition method can handle these non-stationarities. So I think autoregression is good for fast and linear models. Decomposition is better for more flexible, more modular models. So, agenda for today, we're going to basically divide the talk into 4 parts. We're going to check out Formula 1 data. We're going to look at how to decompose its time series. We're going to look at seasonality, always a very important component in time series. And as a bonus, we have a sneak peek into multi-level models. So this is the Japan Grand Prix earlier this year. We see Max Verstappen heading from pole position. We see the 2 orange McLarens after that, followed by the Ferrari of Leclerc. We're going to use the data of this race to explore our framework of time series. So let's have a look at the lap times of this race. What we see here is the lap times over the 53 laps that we had in this race. And there's a few things that we might notice. First of all, there's a huge peak in this data set. This is where the pit stop has been made, always very important in the Formula 1 race. And we can see also different color dots. We see the yellow dots at the beginning of the race. This is the first stint driven on the medium tires, and then the second stint was driven on the white hard tires. I chose 3 drivers here to compare, Verstappen, Norris, and Leclerc. And I did that partially because they all run the exact same strategy, so it's very easy to compare. But the models that we're creating works for any strategy, so we can also compare drivers who drove different strategies. So we see the pit stop. When we remove the data points of the pit stop, we have a bit of a better look at this data. What we see is a downward trend, because over the time of the race, the lap times actually go down. It's around 3 seconds faster that these cars lap around this track at the end compared to the beginning of the race. And that's something we're going to model in a second. Here we see 1 data point per lap, but Formula 1 actually generates lots more data points per lap. So we can also look at the telemetry data. What we see here is the 3 fastest laps of these 3 drivers that I just introduced over the course of this race. We see it plotted out over the track. We see different drivers are fast in different parts of the track. And we can see the speed readout over this specific lap, where we can see they start on the straight, they go faster, reach their top speed, have like a hard braking zone where they really reduce their speed, and this is how they progress through the lap. This is the data that we're going to use to model the concept of seasonality later on. But first, the decomposition of time series. This is the time series I just showed on the screen, and there's different components that either make the car go faster, go slower, or have an unknown effect. It can be either way. Fuel burn makes the car go faster. These cars start with around 105 kilos of fuel. They used most of it during the race, so the cars get lighter and therefore faster. There's also track evolution. The tires wear out. This rubber actually sticks to the asphalt, which makes the track go faster over time. And whenever they get fresh tires, they have a jump in performance because they go from old tires to new tires, makes them faster. These tires, however, make them go slower over time because we have tire degradation. We're going to find out how much exactly. And also the pit stop, of course, what we saw in the example, takes around 20-25 seconds. But it's mandatory to have at least 1 in every race. So we cannot disregard it. We want to model it. And then there's unknown factors such as asphalt temperatures. Higher temperatures typically means more grip, but maybe also more tire wear, so it's not always obvious what it does to the performance of the car. And of course, there's external elements like the weather. It can be rainy, it can be sunny, it can be cloudy, all affect the performance of these cars. So let's start modeling. Here we have the first Bayesian model on the screen. We model our y as a normal distribution centered on mu with a certain sigma. Our mu is our formula in this function. It's basically a very simple linear regression type model where we have an intercept alpha and then a beta, which is the slope per lap that it goes faster, multiplied by the amount of laps. And we have 3 prior distributions, alpha, beta, and sigma, that we're going to sample from. This is how it looks in code in PyMC, the framework that we're using. And we can see what this model does when we estimate it. We see here 3 distributions. If you've used PyMC before, you're familiar with these graphs. And what we basically see is how much faster these cars go per lap. You can see it on the screen. It's around 0.06 seconds of a slope that we find, there is some uncertainty in there that's built in the method. And that's the first thing that we learn. So if we draw the regression line into our data, then we see it goes down. But is it a very good fit? I would say it's not perfect yet. It seems to be a bit more steep. We know that we have 2 pit stops, so let's include that as well in our model. We have different tires. Different tires have different grip level and different degradations, so we add this as an additive component to our model. Here we add a gamma to the model. In the code, it looks like this. 2 extra lines, 1 for the prior, and we extend our model definition with a gamma. We also put the compound index there because we actually add 2 different gammas, 1 for the medium tire and 1 for the hard tire. And when we estimate this, we get this as a result. We see 1 extra line of graphs where we can compare what happened with this medium and this hard tire. We see actually that the trend line became a little bit steeper even, because now we have like an additive component that makes the car go slower. It's around 0.01 to 0.04 for the blue graph, which is the hard tire in this case. And then the medium tire, displayed in orange, degrades faster, is what we can see. That's what our model has learned. And it's also in line what we expect, what we know as a Formula 1 fan. Looking at how our model fits now, we have a sort of structural break in our data. In the middle graph, we see the original trend line and how the structural breaks makes it different. And at the bottom, we see the residuals or the noise, the unmodeled variance that we still have left in our model. Thirdly, let's have a look at outliers. They are almost in every data set. Here, they are in the form of 3 different things. We have a pit stop. A pit stop actually consists of 2 components. We have an in-lap. That's the lap where the car drives a little bit of extra road to go to the pit straight. And then we have the out-lap, which also typically contains the actual stop, and then the first lap on the new tires. Here we see that these 2 are outliers in our data set. And also the start of the race is an outlier. Here we see the number 1, 2, and 4 from a qualifying point of view. And it seems that there's a linear relationship between the starting grid and the additional time you take to complete your first lap. So let's model this. We add 3 different components to our model. A delta for the starting position, multiplied by the grid position. The delta for the in-lap, delta for the out-lap. This is how it looks in code. Again, 3 different priors and 3 added components to the model. And when we estimate this, we see this. We get 3 new graphs, and we find out that the start is around 0.7 seconds to 1 second additional time that it takes per grid position that you have to complete the first lap. We also see that the in-lap doesn't take that much time. Here in Suzuka, Japan, it takes 1.6 to 2.4 seconds. But the out-lap, the lap where the pit stop is actually made, is around 21.5, 22 seconds. Maybe also different per team, maybe different per driver, who knows. But this is sort of the first part of the talk where we make a time series decomposition. Here we see it in its complete overview. We started with a time series on lap times with an outlier. We model the trend, we add structural breaks to it, we add outliers to it, and we end up with just the noise of the model. Then let's talk about seasonality. I already introduced it at the beginning. We have telemetry data, very interesting data set. You can compare all kinds of things between drivers. We already see the red line and the blue line and the orange line sort of deviating a little bit from each other. But let's model the telemetry data over 1 stint. This is the stint of Max Verstappen, first one on its medium tires. And if we look at this time series of this whole telemetry readout of around 20 laps, we see like a repeating pattern, and let's see if we can model this. To do so, we first overlay them all on top of each other to get this telemetry data, and we can model this using a specific trick. This trick is called radial basis functions, and it gives us the ability to make a linear combination of components that ends up modeling a very highly nonlinear curve. We do so by adding these components. Here from left to right, you can see that we have 3 kernels as a start: the blue one, the yellow, the orange one, and the green one. We can change the amplitudes of these kernels. Those will be the coefficients that we're going to estimate. And when we add them all up together, we get like the black line. That's going to be the model that we end up with. We do this over the entire feature space of our input feature. Here I have made 2 of them, both with 10 radial basis functions. The one on the left is a bit wider. The one on the right is a bit more narrow. And together, they should be able to find nonlinear patterns. We've done this for our model. Actually, I took 100 wide ones and 100 narrow ones. That sounds like a lot, but it can be a starting point to model this type of curve. We also see that lots of them actually have a coefficient centered around 0. So you can use the strategy of backwards elimination by, again, removing radial basis functions that don't add to the result of the model. And with that, you can remove a lot of them and still have a good result. So how well does this fit? This was the original data. And now we add the learned seasonality on top. It's almost perfect. You see like a few different places where it's not. We can look at the residuals to observe, like, hey, how good is this model fit? One of the things that I noticed was I expected it to be like a little bit off here at the end, where you see like the little bump. That was for sure not the biggest thing that was off. It's mostly in the braking zones. That's where the deceleration is so big that from data point to data point, you can actually have a really big difference. This maybe has to do with the way this data is overlaid on top of each other, because I synchronized it in time and not on lab distance, because I didn't have that info. So maybe that's the reason why it doesn't fit it perfectly. Or it can be that because this tire wears out, that you have like a earlier breaking point or a later breaking point, and that the differences come there. Nonetheless, this is a very good fit. Max Verstappen really drove this stint very consistently. You see like no deviations from the general pattern anywhere. If you would have, we would have seen it here in the residuals. So this is what you can use as well to do anomaly detection, to really see where does my data point deviate a lot from what my model is expecting. What we can also do is train our model on the first stint and then use the learned seasonality and combine that with the previous model on the trend and the tires to make a forecast for the second stint. Just an example of what can be done, and probably also what they are doing at the pit wall. They're constantly monitoring what's going on, how these tires change, how these lap times change, what the competition is doing, and so on. Then a small piece on multi-level models. Who of you have ever worked with multi-level models before? Okay, a few of them. Nice. We're going to use it to explore the question, is it a driver or is it a car? A question that people who are into Formula 1 are always like talking about, thinking about. What we're going to do is, so far we've modeled every driver, every team, every tire independently from each other. We actually didn't even distinguish between them. We just said there's one model. We can model them all separately, but then they have no connection. They cannot learn from each other. We actually want to model this in its entirety. To do so, we can use multi-level models, also hierarchical models named, and we do so by adding hyperprior, for example, to the team, to the driver, or to the tire compound. And when we do so, we can model the similarities and the differences simultaneously. So, how does that work? From a conceptual point of view, what we do is, firstly, we make a hyperprior where we put the overall lap time distributions for all drivers for all teams. From that, we sample a lap time per team. We sample that from the overall distribution. So we have a new distribution per team. And then from that, thirdly, we can sample the drivers from the teams that they're actually driving for. So we have a sort of 3-layer deep multi-level model. One of the important things to do here is to normalize the data and to center the data, otherwise your MCMC algorithm will just not sample well from this. When we do so, we end up with this. I'm not going to go into all the details, but just give you an overview of how it looks like. What we're going to look at is a few different parameters that we've learned here. We have the alpha driver, which is basically the mean performance of each driver controlled for team. Then we have the alpha for the team, which is the mean performance of each team controlled for the driver, since we're doing it simultaneously. And then the sigma alpha driver, sigma alpha team tell us something about how much the drivers and team vary amongst each other. And with this model, we can now ask questions like, which driver outperforms relative to their car, or which teams are generally stronger despite having either weaker or stronger drivers. So let's have a look at which conclusions we can draw from this data. On top, we have the overall lap time. These are all the intercepts of the models, the alphas. In blue, we see the overall one. Then in the second layer, we see per team. We see an orange line, a green line, and a blue line. We see that the orange line has an offset a little bit to the left. That means that the orange line, in this case, it actually represents McLaren, has the stronger car for this race, which also very well reflects what's happening in this season. If you're following along, the McLaren is the dominant car this year. And even though the model is not very certain, we only use a very limited number of data points, we can already see that the model starts to learn this. If we extend this model and learn from all races this year, we would be even more certain that this is the case. Then if we go to the lowest level, we see the offsets per driver. Here we see like a bit more spread in the distribution. On the very left side, we see Max Verstappen really outperforming his car this year, also specifically in this race. On the right side, we see Yuki's line. This was his first race for Red Bull. It was the third race of the season. There was really a big difference between these drivers, and that is represented here in the graph. We also see that the two McLaren drivers are very close to each other. I think we can see it here in green and red for the ones who can see it. These lines are basically on top of each other. It's very hard to distinguish. They also finished this race seconds away from each other. And then in the bottom graph, in the blue and in the orange, we see the difference between Leclerc and Hamilton. Hamilton's third race of the season, you also see that there's a little bit of difference between them. Maybe not very significantly, but at least the model seems to pick this up here. So, to wrap up, let's see what we can do with these types of models. If we zoom out a little bit, like we've looked at 3 different things, what can we do? Well, we can do simulation and counterfactuals. We can calculate the impact of pit stop strategies halfway through the race, now that we've learned what the impact of tires is and the impact of pit stops. We could hypothetically estimate how a driver would perform in a different car if we use the cross-nested multi-level models. We can use this for forecasting and the decomposition components that we've seen earlier in this talk. We can do anomaly detection to find the outliers that are basically far out of the credible interval after we've subtracted the model from our data. Then a few words on Bayesian best practices, which I didn't all follow during this talk, but I think it's important to at least highlight them at the end. It's important to normalize the input data for stable estimation and sampling. I didn't always do it because it makes the model harder to interpret and you have to sort of denormalize them again. Typically, it is a good idea to do prior predictive checking, simulate from your prior distributions to see what the starting point of your model is, and therefore judge whether you're in the right sort of space to start your sampling procedure. It's a good idea to use the entire posterior distribution. Here, what I often did was I simulated estimations from the posterior and then used the mean to plot these models, but there's more information in there. It's richer than that. For example, you can use the quantiles to ask questions like, how certain are we that a certain driver performs in this certain interval with regards to lap time? And also things like validating out of sample is still very relevant. I didn't use any train test bit, cross-validation, or metrics during this talk because it was not the focus of it, but all these things apply to Bayesian models as well. So I would recommend to do them as well. Then, how do these things compare towards things that you're maybe familiar with? Who of you knows profit? Yeah, quite a few of you. Profit is a very similar thing to what we've just seen. It's a modular additive time series model, which automatically models trends, seasonality, and holidays. What one of the drawbacks is it's a bit less flexible in the formulation of your models. So here we can just write out our mu and type in the formulation that we want. It's a bit harder in profit. You also don't get the posterior uncertainty out of the box. There's probably ways to get it out, but it's not like that by default. We can also compare this to the autoregressive models, like the ARIMA type of models, which typically hold assumptions about stationarity and linearity, which this data just didn't have. You can take first differences and make it stationary. Also, it would break on the irregular interval since it's based on lags. You expect every lag to be the same distance away. If we look at the seasonality data that we looked at, the telemetry data typically arrives every so many milliseconds, but it's not always the same amount of milliseconds. So if you have the assumption that all this data is has the same interval in between these data points, you will make mistakes. And this curve fitting exercise that we did with the radial basis function doesn't hold this assumption. You just see data points over the entire feature space. And then maybe at the end, this looks the most like state space models. It's something I want to learn more about in the future. But there you can have an additive autoregressive component, and you can combine that with multivariate components and decomposition components. So it's basically a mix of all these things together. For sure, something I will look into. To summarize, what have we seen in this talk? We've done like an F1 case study to see how we can strategize based on data, what we can learn, what forecasting we can do. We've looked at fuel-borne track evolution, tire components, driver versus team. We have been looking at Bayesian modeling. We have done linear regression, estimation. We've looked at the uncertainty and even looked at some multi-level models, even though it was very brief. And we've looked at the concept of time series decomposition, how to decompose this into a trend, structural breaks, outliers, how to work with seasonality. This can be done with radial basis functions, can also be done with other methods like Fourier series, which is a combination of cosines and sines, has a similar result. We've looked at anomalies. But in the end, I would say the key takeaway from this talk would be that you can have a very powerful framework with this time series decomposition plus the Bayesian component by modeling this in PyMC. You get a very flexible model specification. You can include specific domain knowledge in your models. We didn't really do it today, but you can use the priors to your advantage. For example, if we know that tires will only wear out over time, we can put a prior that is strictly positive and make sure that the model behaves according to our beliefs of the system. And we obtained uncertainty from these posteriors. That is a very powerful thing in itself. So to end with the resources that I've used, and also gratitude to the open source things that are available on the internet, I've relied heavily on PyMC today, the Python Bayesian modeling framework. Tomorrow on this conference, there's an open source sprint for PyMC. So if you're ever interested in contributing to such a framework, you can do so tomorrow. I think I did 2 years ago, and it was one of the first open source contributions I did. So it's a really nice way to get into that. I've learned a lot from the statistical rethinking course by Richard McElrath. He has a free YouTube course with 20 lectures where he goes over all kinds of Bayesian things. And the book is also a really good one. And then lastly, the fast F1 Python package for me to really make it easy to work with this data, and GP Tempo for the visualizations that I've used. Thank you.
Thanks, Wesley. That was a great talk. We're ready for questions? Oh, yeah. Actually, let's start in the back because you're there already. Thanks.
Hi, thanks for the great talk.
Hi.
So the seasonality thing with the repeating basis function, that's a trick I've always used a lot as well. Thing is, I've never really found anything that's working better. Have you tried other things, or did you try this technique for the seasonality and kind of went, well, works, nice, move on?
So I've tried Fourier series as well, which I mentioned at the end, the sine and cosine. One of the downsides that I found there is that these signs always repeat itself again. So if you try to model a certain system, you will always see sort of like a vibration in your system. So that makes me come back to radial basis functions often. And I actually remember learning about radial basis functions maybe 7, 8 years ago through one of your blogs. So shout out to you as well. Thank you.
Thanks.
Thank you. There's someone in the front, but is there? Okay. Noted. Yes.
Yeah, thanks again for the talk. I saw you were affiliated with KLM, and this was more like your kind of side project, pet project. If you're allowed to disclose, do you expect to implement any of the learnings from this little case study in your work at KLM? How would you use that?
It's actually the other way around. I decided to build this talk on Formula 1 data because of the things I learned at KLM. I'm doing time series forecasting, demand forecasting, basically. And I use this PyMC framework and time series decomposition there to basically make models on the origin-destination level. I was not going to present that here, so I applied the knowledge to the Formula 1 case study and in that way share it.
Thanks. Yeah, you had a question, yes.
Hi, thank you very much for the talk. In terms of the radial basis functions, I always find it interesting, like from a physics background, to think about what like the underlying factors are that actually might be related to the functions we use. But did you have any, or did you consider any approach to motivate the number of basis functions you used, like based on different domain knowledge, or did you solely just look at the extra like information that each function was able to add to the prediction and use that as a basis for choosing how many functions to use?
Yeah, so you can sort of start from two sides. You can either start with as little as possible and build it up from there, add components, sort of localize them well in the position of your time series to capture as much variance as you can, basically. That's typically how I do it, to just extend it until you're like happy with the seasonality pattern that you have. And if you add more, you're starting to overfit. This data was like very clean because we had like the same telemetry readout every lab, but if you add too much, you can overfit your data. Because it was so clean here, and I wanted to create something that was sort of track agnostic, I just started with a lot of them and then removed from them, so more like the backwards elimination technique. And as you saw in the estimation, there were lots centered around 0, so you can easily remove them, re-estimate it. It will change all of them a little bit, of course, but then you can just remove until you're happy with the amount of functions you use. I also experimented with modeling the location of where they are. So now I just put 100 like separated evenly over the entire parameter space or feature space. I also tried experimenting learning the location of these radial basis functions and also the width of these kernels. That was way more complicated. I didn't estimate that well because it's sort of trying to figure out the height, the width, and the location of the radial basis function. And it samples it all randomly, so you get a lot of different possibilities. And I just didn't find it optimizing that well. That's why I reverted back to just applying 100 and then removing.
Thank you.
Yeah.
Thanks. We'll take one last question. Yeah, someone there, yes.
Hey, thanks. I'd like to know more about the breakdown of your thought process on how you're going to build up a model. So starting from scratch, how do you decide what components you want and when you're happy?
It really depends on the time series that I'm looking at, basically. I think components like outliers I typically try to remove first, then look at trend and seasonality. Those are sort of like the main components that I would start with, and then just upgrade each and then all of them until you have a result that you're happy with. I typically also look at, I didn't do that in this talk, but I can slowly highlight that. I typically also look at the sigmas that the model estimates. So here we see the sigma sort of goes from like 0.24 to like 32 with just a trend model. It's like the linear model. And later, when I add a structural component for the tires, you see that the sigma actually goes back a little bit. It goes lower to 0.2 to 0.28. When I'm iterating over the models, I keep an eye on that to sort of learn how much variance it explains and how small we can make the sigma by adding more components next to the typical metrics that you use for model comparison.
Thank you. Okay, let's all thank Wesley again.
Thank you. Oh, nice. Thank you.